Good morning, one and all. Is it audible to all of you? Yeah, thank you. Before starting the trends in MEMS, I will be speaking about introduction to MEMS. So before I start the session, let me introduce myself, Dr. D.V. Manjunatha. I am the coordinator for AICT ATAL FDP. December 2021, which is being started today, and it will go up to next 5 days. So before I start my session, I just wanted to give some instructions to the participants. The certificates, it is the ATAL FDP's instructions. Certificates will be issued only to the participants who are registered on ATAL portal and attend the program with minimum of 80% attendance and score minimum of 60% in the tests which we conduct every day. Online feedback forms test link will be shared in regular intervals, which should be filled by all the participants without fail. Kindly all of you keep the microphone and camera off and turn only if necessary, as the sessions will be recorded and the same will be sent to AICT. I have updated Google Meet on the ATAL portal. The same link will be useful for all the sessions. Now I'm going to share the screen. Already shared, I think. Is it visible? One or two, is it visible? Yeah. So my today's topic is an introduction to MEMS in the trends in MEMS and nanotechnology. Why we chose this title is because there are enormous works have been carried out both in MEMS and nanotechnology. So this 5 days FDP will be a mix of both MEMS and nanotechnology. So here you will be getting information, introduction to MEMS, the soft MEMS, computing soft MEMS, then MEMS fabrication technology, some examples of vibration sensors, fuel cells, and introduction to nanotechnology, then terahertz nanotechnology, and some introduction to some nanotechnology, fabrication, etc. So let me start with the trends in MEMS. I have taken this part, introduction to MEMS. So I'll be going through these slides. Interest in MEMS, micro electromechanical systems, has grown dramatically in the last decade because of wide range in applications. These include automotive industry, process control, automation, medical, scientific and medical instrumentation, telecommunication, commodity products, environmental monitoring, etc. As a result, MEMS technology has become one of the most rapidly changing fields. Yeah, let me do it in slideshow. So the evaluation of top 10 ranking MEMS vendors by revenue are given in this graph. See, it is starting from 2009 to 19. Who are all the giants in this area? See, the first stands is the Broadcom. Next is Bosch. Then Saint Electronics, Texas Instruments, and etc. So market analyst has not revealed revenue in figures in 2019. Up to 2019, it is marked. Ranking and only through ranking by top 10 market share. This puts Broadcom and Bosch in about first place, followed by Saint Microelectronics, Texas Instruments, etc. The ranking stays same as 2018. Corvo fifth, followed by Hewlett Packard, Of course, these are the information which I have taken recently from the Google. If you can Google also, you can get it. But still, it is my duty to introduce trends of MEMS before going to introduction of MEMS. So, Chinese components company 9 TDK drops 10th, Panasonic falls of the top 10, right? So this is just statistics in MEMS I am giving. Next 5 years, starting from 2001 to 2021 to 2026, the whole market will be grabbed by the MEMS and NEMS technology, MEMS and nanotechnology. It is around $400, 400 billion business will happen for the MEMS and nanotechnology. So we have chosen this as the topic. The value of global MEMS and sensor market will almost double from $48 billion to 2018 to the year 2018. MEMS and sensor market represented the more than 10% of total IC market. As more and more MEMS devices and sensors such as MEMS, image sensors, RF filters are integrated in end products in consumer and automotive areas. In particular, the value of MEMS only market reached $11.6 billion in 2018, with consumer applications accounting for more than 60% of the total market from 2019 to 24. The MEMS market will grow 8.3% annually in value, driven by pressure, RF, and inertial and future MEMS. Right? So this is the actual market of MEMS. So if you see this graph, inkjet, what are all the areas in MEMS? What are all the applications in MEMS? What are the applications of MEMS? Inkjet heads, gyroscopes, micro bolometers, pressure sensors, digital compass, PIR, thermopiles, microphones, inertial combos, microfluidics, accelerometers, optical MEMS, RF MEMS, etc. will grab the entire market from starting from 2018. Now we are at the middle 2021. By 2024, all these are the major areas of MEMS which grabs the entire market by the values which I told in the last slide. During 2018, all foundries saw their revenue increase. Saint Microelectronics, Teledyne, Tesla, Selex, and with Innovative Service are important MEMS foundry players that offer services to various MEMS devices used in medical and industrial markets, among others. On the other hand, medical applications were driven mostly by microfluidics of MEMS area, flow meters, pressures, sensors, and inertial MEMS. On the other hand, industrial applications were driven by inkjet heads, microbolometers, and pressure MEMS. The market prospect, however, is huge for RF MEMS and oscillators that will be used in the next generation 5G infrastructure. Right? So coming to this slide, see, there are 5 sense organs for any human, right? All those sense organs are grabbed, and like the human, the sensors will work today. So the 5 sensors are sight, body balance, audio, smell, focus, taste, speech, right? All these are the sense organs, right? All these are grabbed by, see, CMOS image sensor, and then microbolometers, micromirrors works as a sight of a human being, which are sensors. Likewise, body balance can be done by inertial systems. Audio is managed by microphones. Fluidics manages the not accessible to human capability, but it will be handled by biochips and micro pumps. Sorry. So smell will be catched by gas sensors, electronics noses for VOC, alcohol, etc. Focus is done by autofocus devices. Taste will be sensed by humidity sensors, speech, microspeakers, pressure sensors, touch, force haptic and touch sensors. So many sensors. You tell me today, what do you want to do for those aspects? There are sensors available. So whatever the human mankind is doing, all those sensing applications are available in MEMS sensors. So MEMS sensors capture the whole market starting from 2014 till 2019. It has grabbed the sensors like anything, right? Grabbed the market in the area of sensors. So all of you are very curious to know what are these, what is this technology of MEMS? So let me introduce today to all of you the MEMS, introduction to MEMS. What is this MEMS? An integrated system of micro devices consisting of some smallest commercially produced machines, emerging technology combining multiple physics disciplines, similar to traditional sensors and actuators, but much smaller. Complete systems are typically a few millimeters across. Features and components are of the order of 1 to 100 micrometers. Micrometer, you cannot even see through your naked eyes, but they will do a lot of work. It brings together silicon-based microelectronics with micro-machining technology. So there are two technologies here. One is related to electronics, silicon-based microelectronics. The other one is related to mechanical micro-machining technology. So these are the two areas which combined and form a micro-electromechanical systems, right? So what are the MEMS? So MEMS, I can say it is interdisciplinary. MEMS has entered into thermal area, fluidic flow, sound, electricity and magnetism, quantum mechanics, chemistry, biology, light, mechanics. See, if you can see mechanics, heat, fluid flow, all these comes under mechanical area, and sound, electricity, magnetism comes in electronics, and quantum mechanics is a physics area, chemistry, biology, and light again optoelectronics. It also comes in electronics. So it is a multidisciplinary. MEMS is a multidisciplinary technology. Today, multidisciplinary technologies grabbing the entire market, because one discipline, if you want to move other, you have to take the help of others, so it will not serve the purpose. So the why the MEMS has increased its potentiality is because MEMS is multidisciplinary, right? So scales matters in MEMS technology. So Himalaya, height of Himalaya approximately 8 kilometers, right? So the height of man is 1.8 meters somewhere, right? So ant size is 3 millimeters in terms of millimeters, right? Hair of a humankind is 75 micrometers of approximate size. Cells, so micrometer falls here. So in this dotted line, in between these two dotted lines, the MEMS technology, micro technology enters, right? So the size of micro MEMS technology lies at somewhere in terms of micrometers, right? So when it comes to nanotechnology, I'll just touch the nanotechnology also here, but other resource persons will introduce in detail the nanotechnology also. So if we take the nanotechnology into consideration, it is less than 100 nanometers is what is called as nanotechnology, right? So the MEMS technology will become NEMS, nano electromechanical systems, when it reaches the size of nano, right? So let us have this small information at this point of time, but later you will be getting the in detail about the nanotechnology by other speakers, right? So you know the tiny ant, which is of a small size, millimeter size, it can carry tons of load, right? Carry loads in several times their body weight. right? So this carpenter ant is shown here at its actual size. The size of the ant is 3 millimeters, but 3 to 5 millimeters, but it takes more than the weight of this ant, right? The load it takes is more than several times the body weight of this ant. So what is the meaning of this diagram here is that when the device is shrinks, it takes a lot of enormous activities. That is the importance which you have to gather from this. Right. Going to history, there was plenty of room at the bottom. It was introduced by Feynman, Richard Feynman's. There is a plenty of room at the bottom. Was presented at the meeting of the American Physical Society in 1959. The talk popularized the growth of micro and nanotechnology in that. So see, it is not a new technology. That's what I wanted to tell you. 1959 itself, the revolution of MEMS and NEMS or nanotechnology has taken place. Right. It has become more popularized after 2007, 2000. Right. From 2002, 2021 today, we have reached enormous heights in the areas of MEMS and nanotechnology. Right. Feynman introduced the possibility of manipulating matter on atomic scale. He was interested in denser computer circuitry and microscopes, which could see things much smaller than is possible. And he introduced the scanning electron microscopes, right? So the MEMS and the nanotechnology can be viewed today by the two major microscopy. They are scanning tunneling microscope and as well as the atomic force microscopy, right? So we'll see all those details in the I will share one video also, the fabrication of video of fabrication somewhere later slide. We'll see that where there you will understand what is the fabrication scenario, right? So he challenged the audience to design and build tiny motor to write information from a page of a book on a surface of 1 by 25,000. That is the size. Very small size. He wanted to put a small one-page book, right? A small book. For each challenge, he offered price of $1,000 for the people, right? Foresight. That's how the technology has grown. Foresight Nanotechnology Institute has been issuing a Feynman Prize in nanotechnology each year since 1997, right? So this is the history of MEMS and NEMS, right? So water bug also, again, water bug is a very small water bug, but it will walk on the water because its size is very small. So that is the information which you can get from this, right? So at the lower weights or lower sizes, you can do wonders. That is the meaning of this particular slide. I'll move on to next one. These are all the, this is a macro structure. This is a mesostructure, microstructure, right? 75 micrometers, right? So fine microstructure is a very small sized nanostructure, that is 1 micrometer or 1 ml micrometer, right? 5 micrometers. So this is the size, it is getting reduced, right? Okay. So we'll see, we'll move on to next slide. History of MEMS dates back to the middle of 20th century. The first application was silicon-based strain gauze, commercialized in 1958. Silicon-based pressure sensor in 1960s. Nozzle for inkjet printers 1970s. Optics, radio frequency, and life sciences in late 90s. MEMS optical networking components become big business in the year 2000. I told you, it has enormously grown from 2002 till date and in future also, right? So that's the point. So 2000 to 2010, lot of MEMS sensors were developed, which have lot of applications in the present scenario in medical, defense, and biomedical engineering. 2010 to till date, still the research is going on to improve the applications of MEMS in various areas. So MEMS is the newest technology which has lot of research avenues. I told you the entire market by 26 will be grabbed by MEMS devices. And MEMS and IoT, they are merging now MEMS and IoT. The MEMS and IoT by 2006, somewhere between 2001 to 2006, will grab the entire, I think, 50 to 60% of the market business by around $400 billion will be grabbed by the MEMS and IoT in the whole world. I am talking about, right? So this is the new technology, which is the trends, which is the trending area. So I just highlighted all these points, right? So let us. I think all of you are very curious to know what is MEMS, right? So I will define MEMS in 4 blocks. MEMS is a microsensors. MEMS is a combination of microsensors, microactuators, microstructure, microelectronics. So sensors, MEMS, microsensors measures the physical parameters, microactuator controls the system based on processed data. So the processing can be done by microelectronics. Your electronics lies here, right? So process data generated by microsensors. The microstructures, mechanical structures, wells, pumps, microfluidics plays a very important role in MEMS, right? So MEMS is the technique of combining electrical and mechanical components together on a chip to produce a system of smaller dimensions. So the MEMS combines microelectronics, microsensors, microactuators, microstructures. The microelectronics is very similar to the chips that we think of today, right? Okay. Microelectronics acts as a brain, while sensors and actuators acts as eyes and arms to allow the system to control and sense the environment. So the arms acts as a control system, right, which controls the eyes and the brain. Eyes means actuators and the microelectronics, right, sensors, right. So sensors gather information from the environment. The electronics process this information. The actuators respond by moving and regulating, thereby controlling the environment for a desired outcome, right? So why MEMS? So as we all saw, the size matters at all the places. See, your mobile is today, you can keep it in your hand or you can keep it in your pocket. That is a mini computer nowadays. Earlier in 1970s and all, very big room-sized computers were there, right? So if your mobile is of a big size, can you carry that mobile? No. So portability becomes very important when it comes to the applications of the devices, right? So if the mobile is not reduced its size, you would have not carried that mobile. So every place you are carrying the mobile because of its strengths, right? Its size, minimum size, right? And it also has a lot of features, right? All the features, almost all the features in a small device called mobile, right? All features. It is a mini computer actually, right? So the computers are notebook-sized computers. It has reached an enormous size reduction from a big room-sized computer to a small-sized computer. So the size matters. Miniaturization with no loss of functionality matters. So MEMS gives you miniaturization with no loss of functionality. Integration to form monolithic system. Monolithic means in a IC you can form many peripherals you can combine in a monolithic IC system, right? Integrated circuit. So improved reproducibility means reproducibility, right? So the production is a batch production, batch fabrication. So you cannot manufacture a single MEMS device. So thousands or lakhs of devices can be manufactured at a time. That is called as a batch process, right? So where reliability and accuracy is also very good. So only MEMS people are moving towards, right? Exploration of new physics domains, scientific motivation has occurred due to the MEMS. So, and it since the size is reduced, the power it carry or it can take is also very low. So low power devices plays a very important role. So fast actuation techniques. Actuation can be done very fastly because of size reduction again. So improved selectivity and sensitivity, and MEMS may be the only solution for achieving all these above advantages. So MEMS, why MEMS is, this is the reason, right? So MEMS, different names in different countries, right? Let us know what are MEMS in US. US name is MEMS, Micro Electro Mechanical Systems, but Europeans name is Micro Systems Technology, MST, right? Japanese call this MEMS technology as micro machines or micro mechatronics, right? Nanotechnology is called as NEMS, right? So in Japan, they call it as NEMS, and for nanotechnology, and micro machines or micro mechatronics, they call it as, right? Maybe nano system technology, NST, they will call. Nano electromechanical systems, US, right? So these are the different names in different countries for MEMS, right? How many transistors are there in a latest microprocessor? So this is a small question, but anyway, I have answered this question at 1.3 billion transistors. See, if you put a small dot, 10 transistors can be formed in today's technology. If we speak about in terms of electronics, right? So that and all is possible due to MEMS and nanotechnology, right? So miniaturization has been the driving force of electronics, and that is entering mechanical and many other fields. So miniature is not a new topic in electronics. Under VLSI, very large scale integration, all of us know that it has reached a very tremendous applications of VLSI, right? So we are, as electronics people, we know very large scale integration that is been achieved. That is the miniaturization has been achieved with the help of VLSI in electronics, right? And that VLSI has entered into mechanical also. And together, this IC technology as well as the mechanical and many other fields are combined and forms a MEMS, micro electromechanical systems, right? So advantages of MEMS. What are the advantages? So we have seen the why MEMS is required, right? So what are the advantages? Entire systems can be miniaturized, reduced manufacturing cost due to mass production, high reliability, precision, and functionality of the systems. Large number of MEMS devices fit in small area. Low power consumption. Major advantage is the portability. We can take it to any place, anywhere in this world, right? So that is the advantages. These are the advantages of MEMS devices. Some of the interesting MEMS examples are a gear chain. See, you have seen MEMS gearing system in nowadays new cars. MEMS gearing systems have been used. See, you write a small line on the road, a line on the road. On the road, you can stop the car by a system called as MEMS braking system, right? Which is called as an electronic braking system, they will say, but they will use some MEMS technology there, right? Gearing system, you can easily turn to very high speed from starting from 20, 30 speed to 180, 200. That enormous speeds can be achieved with the MEMS gearing system. So gear chain is used in MEMS gearing systems. Similarly, a sensor web. So sensors, I should not say anything about sensors because sensors has entered a lot of applications today, right? So coming to micro steam engine in mechanical area. So there is an electronic tongue which tastes the smell, which tastes the thing, right? So that is an electronic tongue, which is still research is going on that. Next, we'll move on to a smallest car, world's smallest car sitting on a coin, right? The car is 4.8 millimeter long and runs on a 0.67 millimeter electric wake motor, right? So this is the smallest car in the world, right? So the smallest guitar, so even it has entered into musical system also, right? So this is the example, right? Next, xenon atoms, 35 xenon atoms are placed here, right? Atomic level, the MEMS devices works, or electronic level, the MEMS devices are working. So only the technology has grown like anything, right? So coming to micro, macro, micro, nano, what are the differences? Right, macro are conventional machines. So you can see a lot of machines in your car or anywhere, right? So which is of the size of meter to millimeter size, right? So micro machines, we call it in terms of mechanical, we call it as a micro machines. So zero point 0.1 millimeter to zero point 0.1 micrometer. So a lot of miniaturization happens from this big system to a small micro machines. And nano means it is 100 to 1 nanometers, 100 millimeter to 1 nanometer. So this is a nanometer nanosystems, right? So what is the block diagram of a microsystem? Right, the block diagram anyway, it requires power supply. Any device requires a power supply, right? So signal transduction and processing unit, it is usually an electronic system, actuator and sensor. As we already discussed, what are the parts of MEMS? So electronic part, sensor, then actuator is a control system which is from the mechanical, right? So when it comes to a MEMS system, physical world is sensed by sensor and is given to MEMS transducers. Signal processing happens electronically and it will be given to actuator back to accomplish task, right? Sensor, electronics, actuator. These are the three things which will be there in the MEMS devices, right? Next, microfabrication process. So when we will come to microfabrication, right? So slowly, so far I introduced what is MEMS, what are the advantages of MEMS, what are the why MEMS is required, and then what is the size of MEMS, what is the block diagram of MEMS, and then now we will move on to how the manufacturing fabrication means manufacturing of MEMS devices can be done, right? So we call electronically all electronic parts. See, you know that by this time, processing can be done electronically, right? So electronics means it is IC process. So there are two processes in fabrication of MEMS devices. One is the IC processes used to fabricate electronic parts. Example, CMOS, bipolar, BiCMOS process. So the processing can be done by IC process sequence, which is a fabrication of VLSI, etc. Then mechanical parts can be fabricated using a term called as micro machining process. Micro machining process used to fabricate micro mechanical components like sensors and actuators, right? So micro fabrication, we will go in detail into the micro fabrication IC processes, micro machining processes, right? So can we, okay, there is a video which I wanted to play. Okay, once I'll introduce the fabrication, I will play the video. There you will understand how the doping, film deposition, mask making, patterning means lithography, etching, bonding, processes of IC design. It is somewhat related to VLSI. If you are electronic faculty, you will be knowing what is doping, film deposition, mask making, patterning, etching, bonding, etc. Right? So these are all the VLSI terminologies. When it comes to micro machining processes, surface micro machining, depositing and patterning of layers on a wafer, right? Wafer is a holding material, you know that, silicon wafer. We'll see that later, right? So bulk micro machining is another method. There are two types of micro machining processes. To do depositing and patterning layers on a wafer, we go for surface micro machining. To etch out some materials or to bond the entire wafers, we go for bulk micro machining, right? So we'll move on to next slide. The film deposition, grow a thin layer on the top of a material. Common methods used are oxidation, LPCVD, chemical vapor deposition techniques, right? Sputtering is another methodology, right? Example, oxidation, silicon dioxide, LPCVD, silicon nitrate, right? So next, mask making. What is mask making? Process of defining patterns that will be transferred to your masks. So why mask? Mask is required, right? So you have to transfer the patternings onto the wafer. So to do that, mask is required in the fabrication. These are the fabrication steps, right? So pattern transfer, patterned silicon, patterned using photolithography, right? A window should be opened by using a technology called photolithography, and subsequent etch method we have to use. There are so many methods available, out of which I have named three here: ruby lithography, pattern generation, e-beam lithography, etc. So mask substrate, soda, lime glass, and quartz they are using for mask as a mask substrate, right? So mask coating, the two most commonly used mask coating materials used for optical lithography are emulsion and chrome, right? So this is a methodology called as photolithography. See, this is the silicon wafer, right? See here, I wanted to introduce polysilicon here and photoresist here, and I want to etch out this particular portion. I am showing in the mouse arrow here. So please concentrate on this part. I want to etch out this portion. So we will be going for a photography. So photolithography. Photoresist is applied on the surface of the wafer. This is a silicon wafer on which silicon dioxide is grown, upon which silicon nitrate is put. On that photoresist, which is a opaque, oily kind of material which is placed on the entire surface of the wafer, and there we will be putting a mask. This is a mask actually. This entire thing is a mask. This is a opaque region. This is a transparent region. Then we will pass the light on the mask, and wherever transparent area is there, light falls. Other opaque area, this dark area, light will not pass, right? So this opaque area, light, this portion is not exposed to light. This becomes hard only. This portion will be hard, and this becomes smoother part, right? So wherever light, UV light is exposed, that becomes very smooth, so that can be etched out by etching techniques. The steps involved in photolithography are photoresist application, layer photoresist, expose photoresist using mask to the UV light, develop the photoresist, and pattern a layer using a mask, right? Remaining PR will protect the underlying layers, while the others are etched out. This portion is etched out, right? This is how the transistors are formed, right? Okay, we'll see that later. Okay, etching. What are the different types of etching? Etching means removal of unwanted material from the substrate, right? That can be done by using two methods. One is wet etching and dry etching. The chemical etchant dissolves one material but not the other material. So this concept has been taken, and the substrates are immersed in a etchant. Etchant is a material which etches out the smoother parts of the wafer, right? Chemical etchant dissolves one material but not the other materials. This is a cheaper technology to etch out the unwanted material from the wafer, right? So dry etching is bombarding the material with ions or gas. Plasma and RIE are the two major methods. This gives high aspect ratio, but you cannot expect high accuracy in wet etching. But very good etching, very good accuracy can be obtained from dry etching. So these are the diagrams. So we will put some, we'll immerse the wafers into the chemical solution, and we will take out required part from the wafer. Isotropic and anisotropic etching. There are again two types of etching methods. We'll not go in detail into all this, right? So we'll move on to next slide. Wafer bonding. See, wafer bonding means, see, electronics and mechanical you have to combine in MEMS devices. So electronic part will be done on IC technology on one wafer. Mechanical micro machining can be done on another wafer. Both of them we have to bond. So that is called as a wafer bonding. Silicon and glass wafers may be bonded together to create more complex structures. So there are so many methods available. Anodic bonding, silicon glass, fusion bonding, silicon silicon, right? If you want to combine two wafers made up of silicon, you can go for fusion bondings. If you want to combine the glass wafer with the silicon wafer and bond, that anodic bonding can be done. So bonding using intermediate layer. So silicon, glass, silicon is a intermediate bonding using intermediate layer. So silicon, glass, and silicon is a major bonding methodology used in adopted in MEMS, right? Microsystems may be bonded to CMOS wafers, right? CMOS wafers, microsystems can be bonded, right? Okay, so this is the wafer bonding. How fabricate. Before we go to this fabrication, or after the fabrication, I will be putting a video where you will understand what is this micro fabrication, right? So deposition, very frequently we do the deposition, then lithography, exposing the wafer to the light by using a mask, right? Etching can be done, and then bonding can be done. These are the four steps which will be involved in microfabrication: the deposition, the lithography, etching, and bonding, right? So surface micromachining. What is surface micromachining? On the surface, you have to introduce some material, right? So that is a surface micromachining. So this can be done most of the time on mechanical parts. Deposit sacrificial layer, right? And then pattern the contacts. How do you do the patterning? Patterning can be done by using lithography, photolithography, right? Pattern structural layer, right? So you have to put some structural layer here. So that can be done. Then etch out the sacrificial layer or the patterned this thing. So you can get a structure like this, right? So most of the time in all the fabrication, many times we repeat the photolithography and etching processes and deposition processes and then bonding processes, right? So this is the micro surface micromachining. Then bulk micromachining, there are two types of two etchants we use. Anisotropic KOH etching liquid and isotropic plasma etching. These are the two methods which we use in bulk micromachining. Non-conventional techniques. So there are again conventional techniques and non-conventional techniques. These are all the fabrication details. If you want to get understood by this fabrication subjects you have to handle, and many fabrication foundries you have to visit, then you will understand all this very well, right? So electroplating is a method called as Liga. Liga technology is used in conventional techniques. Photolithography of all molds using X-rays, electroplating in mold, right? Tall structures, we use conventional techniques, right? So this is one of the Liga technique. Irradiation, development. Third step is electroforming. Fourth step is mold insert. For fifth step is mold filling, and then mold release. These are all the techniques used in different steps used in Liga technology, right? This is a non-conventional. Okay, non-conventional techniques, right? Conventional techniques means normal techniques we use. That's a conventional technique, right? So what are the differences between conventional and non-conventional techniques? Before I go to this, let us see the video and come back, right? So I request all the audience to go through the video very well, and then we will come back, right? Okay, thank you. Just 1 second, please wait. I will now share the video. ವಿಡಿಯೋ ಆಗ್ತಾ ಇದೆಯಾ? ಮಾಡಿದೆ
which is supported at one end only. It may carry a load.
So this is a cantilever and SY wafer.
Next, let's identify the broad microfabrication technology we shall employ, which is surface micromachining.
See, I told you bulk micromachining, surface micromachining.
A silicon on insulator or soy wafer, which is a 3-layer material stack composed of the following. On top, a mechanically captive device layer made of prime quality silicon. Intermediately, a buried sacrificial layer of silicon dioxide or MEMS. This electrically insulating intermediate layer is selectively etched. At the bottom, a support wafer or handle of bulk silicon. Our soy wafer has a 1 micron thick silicon dioxide layer buried under 200 nanometers of silicon layer.
So cleaning details, right?
We initiate MEMS cantilever fabrication by cleaning the soy wafer. This
so
is
clean rooms plays a very
in
important
wet-etch
role
way.
in the fabrication.
First, we place the samples in a wafer holder and dip it in the piranha bath of the wet bench. The samples are kept in the solution for 10 minutes. The piranha solution removes any organic and metallic contaminants from wafer surfaces. The solution is prepared by mixing sulfuric acid and hydrogen peroxide in a 9:1 ratio by volume. 10 minutes later, we remove the samples and rinse thoroughly with deionized water. This is followed by blow drying the samples.
So this is
with nitrogen.
The fabrication of cantilever. I will come to that cantilever. Just know the details of the fabrication, how practically the fabrication can be done. So photolithography, I told. So this is a photolithography. They are
For the next step, we move to the lithography bay, which has a cleanliness level of class 100. Here, we shall transfer
I will tell you what is class 100,
right? From a glass mask onto the cleaned wafers. First, we dehydrate the samples at 250 degrees Celsius for 10 minutes to remove surface moisture. Next, we spin coat the wafer's device layer with photosensitive resist of nearly 1 micron thickness.
So photoresist is applied on the wafer.
Causes the liquid photoresist to spread uniformly on the wafer surface due to centrifugal forces. In this 3-dimensional model, we see that the photoresist layer covers the entire device layer in even thickness. We now move the resist-coated samples for soft baking on an adjacent table. Soft baking is done at 95 degrees Celsius to evaporate the solvents in the photoresist. The soft-baked photoresist will not stick to the glass mask during the next step. In a similar way, we process the entire batch of wafers. We are now ready for cantilever pattern transfer, which takes place on a separate workstation. NNFC has an EVG double-sided mask liner. First, we pick a cantilever mask prefabricated especially for INUP from our mask library on the wafer. Now the assembly is ready for ultraviolet exposure. UV light exposure is done at predefined energy levels specified in millijoules per centimeter square. After UV exposure, we must develop the pattern on the sample's photoresist. For this, a specified developing solution is taken in a Petri dish. Next, we place the UV exposed samples in the developing solution. The photoresist now contains exposed and unexposed areas. The exposed part is soluble in the developing solution. Therefore, it dissolves, leaving behind a replica of the mask
etching
pattern.
can be done by
Once the
making a
pattern is
patterning of
developed, the sample
using
is rinsed with
photolithography,
DI water,
and
dipped
wherever
in
selectively we can
dry.
etch out the
We
materials
have
using
now created the
photolithography.
cantilever pattern on our sample's photoresist layer. To confirm, we make a quick microscopic inspection. The cantilever pattern shows up clearly on the microscope's display screen.
So cantilever is a beam which is fixed at one end. The other end is free. So we'll see that. Dry etch, I told you, anisotropic plasma etch of silicon. Dry etching.
The next stage of cantilever fabrication takes place in the dry etch bay. Here we employ the ICP RIE fluorine chemistry tube. Next, we place the samples on the carrier wafer. We now load the samples into the RIE. Samples are transported into the RIE main chamber. Gases start flowing inside the chamber at specified flow rates and temperature. Plasma strikes when appropriate conditions are reached. For our device layer of 200 nanometers, we have specified an etching time of 2 minutes. Let's understand in depth what happens inside the system. We are now watching the sample in an ions and plasma environment. Fluorine ions in the plasma start etching the exposed silicon following a chemical reaction. After etching, we unload the samples from the RIE equipment. Since the bottom surface of the sample has formalin oil, we wipe it away with lint-free cloth. We now have the cantilever pattern on the device and photoresist layers. To remove the samples are then placed inside the solution. The liberated color confirms removal of the resist from the sample surface. This takes
So photoresist should not be there on the finished
attacks the resist material,
chip, so which will be
from
removed
the wafer surface
by dipping it in a solution.
Consequently, the samples now contain a patterned device layer over oxide. After photoresist removal, samples are rinsed with deionized water and blow dried with nitrogen.
So wet etching, I told you, ion.
Next, we come to the critical. The BHF solution has been previously prepared at the NNFC to etch at the desired rate. Since the anchor regions are much larger than the beam regions, some oxide remains intact under the anchors after isotropic wet etch, creating a suspended cantilever anchored to the substrate. This is followed by a rinse with DI water and isopropyl alcohol. Here, care is taken to let samples remain in liquid. Otherwise, chances of stiction or cantilevers sticking to the substrate are high.
So the observation of etched cantilevers can be done by microscopy.
To inspect the released cantilevers, we move to the lithography bay, which has the Leica microscope. The inspection must be carried out on submerged wafers from the previous step to avoid stiction. The release is confirmed by noticing that the cantilever and the substrate require differential focusing.
So drying. So after drying only the product can be used.
Next, we advance to the step of drying the wafer to expose its inner chamber. Next, we fill the CPD chamber with isopropyl alcohol to immerse the special sample basket. At this stage, exposure of samples to air increases chances of stiction. So we transfer submerged samples along with IPA into the basket with a large spatula. The equipment is turned on. Let's understand the ongoing process better. In supercritical dryer equipment, the IPA is replaced by liquid carbon dioxide. Once critical point conditions are created in the chamber, the distinction between liquid and gaseous phases is lost. As liquid carbon dioxide turns gaseous, the beams are released with minimal stress. As the drying process advances, LED displays indicate its various stages. During fill cycle, liquid carbon dioxide enters, and during heating, the critical condition is reached. After venting, samples are unloaded. We see that the chamber is completely dry, as are the samples. Unloaded samples are then taken to the characterization facility for final performance testing.
So the final performance testing can be done by characterization.
We are now in Doppler vibrometer to verify that cantilever beams have indeed been released and therefore are functional. The laser vibrometer has a source of variable AC voltage that is applied across the samples, top and bottom silicon layers software to analyze vibration data. After placing the sample on the vibrometer, we position the probes to make contact with the cantilever's handle and the beam anchor in the device layer. Then we apply a specified voltage and observe the frequency response of the vibrating cantilever beams. The vibrometer picks up resonant frequencies of the fabricated cantilevers and displays corresponding velocity peaks. This confirms that our beam has successfully created
moves up and down
cantilevers.
When it gets strained.
The vibrometer software also
so I will
allows
stop at this point of time.
Vibration
I will continue with my
such as
PPTs.
first and second by synthesizing a 3D animation from data.
So we'll go back to the PPTs. Hope the PPTs are visible. I shared the PPTs now. So we were seeing the MEMS industry areas. So you have gone through the entire this thing. Was this testing fabrication process, wherein you have come across deposition techniques. You have come across how the photolithography can be done. Photolithography can be done for opening the windows, exactly where exactly we have to etch out the material, where exactly we have to introduce the material. So that can be done by using a very beautiful process called photolithography. You have seen etching. Selectively, you can etch out some materials by using wet etching or dry etching. And then once the etching is done, you will be expose the wafer to drying. Once you do the drying, then you can use for use in applications, right? So these are all the methodology used in foundries, right? So coming to MEMS industry areas, automotive information. You tell what not areas, what not technologies the MEMS has entered into, right? It has entered into almost all areas, right? So coming to next slide, conventional MEMS development cycle. Let us see, identify the device, then R&D, do some R&D, then devise the design, go for a building prototype, then analyze and testing, fabricate the device, analyze and testing, final MEMS device comes, packaging can be done, and then can be used for the applications, right? So this is the conventional MEMS development cycle, which I'm presenting. MEMS design, high level design issues before you start designing MEMS, right? MEMS technology, MEMS, see, this is a technology push and pull market. So time to market is very, very, very essential. If you take more time for manufacturing itself, it becomes very tedious to enter into the market. So the issue here is time to market, right? Time to market plays a very important role. Yeah, in India, not much foundries are available. So the best place for foundry, MEMS foundries, you can see a lot of foundries in Germany and Taiwan and so many other places of other countries, right? So there, in each street or area, there are at least 4 or 5 foundries will be there. So that is the technology advancement in other countries, right? So let us not go into detail into that. MEMS process sequence. So thick films of deeper features, fewer steps, right? So these are all the steps used, multiple processing. Let us not go in detail into all this deposition of material, pattern transfer. Pattern transfer can be done by using photolithography. Removal of material is a etching. So these are all the methods. This I have shown with feedback because many times you will go back to the same processes, right? So removal of underlying materials to release mechanical structures. Then probe testing can be done and sectioning of dies can be done. Individual die can be taken and assembly into package seal will be put. Finally, it is sent for testing. So this is the entire MEMS process sequence. All these things are done in MEMS foundries, right? Okay. So there are so many applications, biomedical applications. The MEMS devices has entered into many applications compared to other types of sensors. MEMS is the golden technology for inertial sensors integrated into medical wearables, right? So MEMS applications related to medical, right? So micro machined transducers applications for medical diagnostics and treatment, right? Blood pressure sensor can be fixed, right? So you can easily find out what is the blood pressure, all those things. This is one slide where it entered into medical applications, right? So catheter angioplasty and angiogram can be done without opening the heart actually today. So by using a MEMS device, right? So this is one of the major applications in the heart cardio department. People are using the MEMS devices for doing the heart operations or putting a shunt into the heart. All those things can be done by using a very nice technology called MEMS and nano applied BME, right? So the micro nano applied BME. So the see, this is how the cholesterol part can be blocked part can be enlarged, and people can get cured their heart related issues, right? So next slide. MEMS micro needles. Suppose the patient, many patients are admitted many 6 months, 7 months, 1 year at at such situations. So manually, if you give the needle every day, two injections or 2, 3 injections are given to the patient, then that itself will make the patient to get a lot of pains. To avoid that, MEMS micro needles has come into picture. So they will put the patch on the tip of the finger, and through that they will introduce the drug. So this is a drug delivery system, MEMS drug delivery systems, MEMS micro needles. This is the best one of the best application in medical area, right? So these are all the needles, okay, through which the medicine can be inserted into the patient. MEMS smart pill, right? So there are so many diabetic patients nowadays. So the pill contains insulin. Whenever the insulin goes low, the automatically the pill will introduce the insulin, so that the patient will be safer side, right? So the diabetic patients will take the MEMS pill, smart pill, and that pill will have the insulin whenever it is required. Whenever the insulin level reduces in the body, automatically that pill will introduce the medicine, right? So this is how drug delivery system in medical area has entered the MEMS smart pill, right? So next, nanobot. So micro PCR duplicate DNA or other proteins can be duplicated in the body of the patient, right? Mechanical applications. When it comes to mechanical applications, micro gripper application is one of the best application when it comes to MEMS and nanotechnology. World's smallest rotary internal combustion engine. See, this is the smallest combustion engine. Earlier, you would have seen big-sized combustion engines. Now it has reduced to a small sized combustion engine, which will take care of the entire vehicle, right? So in infrared movie of minimum engine operation. This is the engine operation which is taken a picture. World's smallest rotary internal combustion engine. Power generation between 100 to 10 to 100 watts. Portable electronic devices can be made. Mechanically powered devices, drilling can be done. Right, power for remote sensing can be done. So one fluid once of fuel will keep the motor running for 2 hours. Once it is optimized, the tiny engine will be able to run at 10 times longer than the conventional lithium-ion battery. So batteries are replaced by MEMS batteries nowadays. Micro rotary engine, batteries are replaced by MEMS batteries, right? Lithium-ion batteries are nowhere in future days to come. People are using. One such research has been done by one of my research scholar on my fuel cells, MEMS fuel cells, right? Direct methanol fuel cells and hydrogen fuel cells. A lot of research is going on here, and Dr. Pinto will be talking on MEMS fuel cells, right? So we'll see all those later. Micro rotary engine, right? So this is one more application. So when it comes to new cars, there are at least, I think, approximately 26 sensors are used in new cars nowadays to help the driver to move the vehicle, right? So at so many places, the electronic braking system contains the MEMS devices, the airbag contains the MEMS devices, the pressure sensors, which are there in the tires to note down the what pressure the tires are having. So many accelerometers for airbag applications. So many MEMS devices are used in nowadays the automobile industry. So molecular motors are very popular in biosensors, right? Biosensors are basically microsensors based for bio or chemical sensing and measurement of bioactivities, right? So micro cantilever as sensors. So I was telling you so far the sensors. So most of the time, cantilevers plays a very important role in the case of sensors. Just now we saw the fabrication of cantilever. Cantilever is a beam which is fixed at one end, the other end is free, right? Whenever the surface of the cantilever gets stress or strain, the cantilever bends, right? You have seen the bending moment also up and down. So that will indicate the sensing applications, right? So physical, chemical, biomedical, environmental sensors are the micro cantilever sensors, right? So the basic concept of cantilever based sensors. So this is a cantilever, unexposed beam and selective coating can be done. So beam exposed to vapor, direction of beam movement, and then yes, it has entered into a lot of medical applications. The surface is mounted with antibodies and antigens. Whenever it plays, it reacts, it bends. So that shows the tuberculosis detection. So the in tuberculosis detection also, we people are using the cantilevers, right? Cantilever sensors, right? Biosensors, most of the time applications of biosensors are in medical area, right? So this is one more example of biosensor which is taken from the internet only again, right? So mass sensors are cantilever acts as a mass sensor also. Whenever the mass is put on the sensor, automatically cantilever bends so that surface tension occurs and the cantilever bends. The bending moment of cantilever says that there is a sensing of mass, right? So applications in power generation also, there are plenty of applications. Micro battery, as I told you, my micro fuel sensors, right? Micro fuels. So that will be talked by Dr. Pinto sir in his talk, right? Another 10 minutes is left for my discussion. So applications in communication. Let us move on to mobile. You have seen you are rotating the mobile. That is due to gyroscope and accelerometers, which is there in the mobile. So there are a lot of applications of MEMS and nanotechnology. Cantilever micro switch, so is one of the application. Micro resonator is another application. Application in terms of wireless sensor networks. So you can see here distributed wireless sensor network. It has entered into computer science. So IoT and MEMS is the future. 5 days, next 5 years is the IoT and MEMS technology. It has entered into cloud computing also. A lot of MEMS applications are there in distributed data networks and cloud computing, IoT devices, IoT Internet of Things, right? So MEMS has entered almost all the fields today. That's why the MEMS is the multidisciplinary technology, right? So next 5 years is the major market for MEMS and IoT devices and cloud computing and then distributed data networks, right? So sensor networks, the vision, push connectivity out of the PC and into the real world can be done by using sensors. Billions of sensors and actuators are there everywhere. Build everything out of CMOS so that each device costs pennies, right? So enable wild new sensing paradigms. See, I have not told you CMOS and MEMS. MEMS CMOS is the next era, we can say. right? So that is the application. Somebody who knows CMOS technology, who knows MEMS, they can develop MEMS and CMOS devices. That is the next generation, next era of MEMS, right? Next 5 years, IoT, MEMS, CMOS, and then wireless distributed network. These are all the areas. If anybody interested to do their PhD, please concentrate on these areas, so that you will get a lot of avenues, right? Development of sensor networks, combination of breakthroughs in MEMS technology, development of low power radio technologies, advances in low power embedded microcontrollers, right? Smart dust communicating with a cubic millimeter computer, right? So MEMS turning non-mobile and mobile devices into a worldwide sensor network. So that is the statement given in the US. US Department of Homeland Security has been exploring ways to deploy sensors nationwide by riding on the existing infrastructure. Utility poles, street lights, traffic signals, weather stations, smartphones, mobiles, laptops, computers, etc. So that means this slide is highlighting it has entered into MEMS devices have entered into almost all the areas, right? So that was 1999. Privacy is dead. Deal with it. Scott McNally, former Sun CEO, he was telling. Now in 2011, in 2011, the quote should be: "Privacy is dead. Enjoy it. Don't break it. Break the law, and you have nothing to fear." Sensors everywhere means no gunshot would go unlocated. No cry for help will get unheard, right? No bad guy will go uncaught. So my house is protected with sensors and cameras made so cheap I can afford a lot of them. That's good, right? So actually, nowadays home automations are being done, right? Home automations, a lot of avenues are there for home automation. Every home is getting automated to protect themselves, right? Security purpose, right? So home automation is again a best example for a MEMS devices usage, right? Nanotechnology versus MEMS. So nanotechnology meets MEMS, right? Nano cantilever as nano cantilevers are coming are there in the nanotechnology. People are using those to again shrink the size, right? Single cell on cantilever, right? So at cell level, you can deal with resonance shift due to single cell can be achieved, right? ANSYS MEMS modeling and the simulation softwares, right? So we have a research lab, MEMS research lab in our college, Alva Institute of Engineering and Technology, which uses Coventerware tool, which is one of the virtual fabrication tool, and COMSOL multiphysics we have, and these are all other tools, right? Why micro cantilevers? Simplest MEMS devices, right? So lot of advantages are there. Time is getting close. So cantilevers, you can see a lot of information on the Google, right? So these are offering increased reliability, can be easily integrated with on-chip electronic circuitry, provide amplified mechanical readouts. Micro cantilever array can act as a multi-element sensor simultaneously. So mass, surface stress, biomolecular interaction, thermal action, chemical property stress. I told you surface stress can be created by using chemical properties, and so the cantilever bends either upwards or downwards, which you saw in the video. The cantilever bends up or down, right? So the external electric and magnetic fields, thermal effects, good thermal effects by using micro cantilevers. So these are all the advantages of cantilevers. Sensors, mechanical, mass, temperature, heat. These are all the applications of calorimetric sensors, viscosity, stress sensors, IR sensors, chemical, metal ion, explosive, humidity, pH, herbicide sensors, biomedical cancer detection sensors, blood parameters, coronary heart disease sensors, miscellaneous telemetry sensors, magnetic breath detection, beat detection sensors, right? So there are so many sensors. The silicon dioxide cantilever fabricated in Sense IAC Bangalore. This was the taken from one of the Google. Some measurements in micro nano domain, right? So AFM tip, I was telling you, atomic force tip microscopy can be used to used for characterization. Scanning tunneling microscopy can also be used to characterize, right? AFM tip fabricated at Sense ISC Bangalore. AFM Department of ENC. Okay, the position sensitive detector sensors sample surface. See here, diode laser is used to sense the cantilever working. So this is the AFM and STM scanning tunneling microscopy are used to characterize the device after fabrication, right? Some AFM pictures are shown here. AFM applications, surface imaging, surface stress, force measurement, macro mechanics, right molecules, right biological studies, etc. So conclusions. So what are the conclusions out of this discussion? Another 3 minutes is there. I may extend up to 4 or 5 minutes. MEMS are logical extension of silicon fab techniques. I told you, VLSI, those who knows fabrication, VLSI fabrication, it is very easy for them to catch hold of MEMS technology. Into the real mechanical devices, right? MEMS are potential design issues in engineering of near future. Micro cantilevers are promising many sensing systems. MEMS will continue to grow similar to ICs, right? MEMS will integrate with micro nano electronics to provide today's complicated electromechanical systems on a single chip, right? So potential for additional applications is also very exciting. Novel sensors, data storage, power generation are the some more applications. The application and growth of MEMS and NEMS are endless today, right? Okay. So micro electromechanical systems technology has been identified as one of the trending area and most promising area technologies in the next century for potential in making smaller, lighter, and more functional electromechanical devices. Yeah, I'm sorry, there was some. I'm sorry, there was some connection problem. So I will repeat whatever I did last slide. Okay. The last slide, whatever I did, I will go back. So previous slide. Yeah. So I was telling you the MEMS applications, micro electromechanical systems technology has been identified as one of the most promising technologies in the next century for its potential in making smaller, lighter, and more functional electromechanical devices and machines at lower costs. MEMS is the new technology. Of course, it's not a new technology. We have entered into this leveraging the enormous capital investment in IC fabrication technology. MEMS devices are already emerging as products in both commercial defense markets such as automotive, aerospace, medical, and so on, henceforth. Instrumentation, office equipment, appliances, and telecommunications. MEMS products include airbag, crash sensors, pressure sensors, inkjet printer heads, MEMS gearing systems, smart pill, etc. The technology uses silicon microfabrication technology with other advanced precision machining technologies as the main tool to realize various novel designs of micro machines and devices, right? So what is the current status of MEMS for automotive applications? What are the related market drives, right? So I request any participant to answer this question. So it was not so interactive so far. So I request any one of you can answer this question if possible, right? Um, okay, if not, I will continue. Um, so what is the question? What is the current status of MEMS for automotive applications? What are the related market drives, right? Drivers. So the answer is in automotive applications, accelerometers and pressure sensors are still account for the lion's share in the units, right? Pressure sensors grow more than 8% with tire pressure monitoring and implemented in Chinese vehicles in the near future. So 2019-20 with new Chinese standard GB 2614 TPMS will become compulsory 100% for all new vehicles. Right, automotive MEMS could grow quicker than the corresponding car market, currently approximately 3%. The reason is higher number of many different MEMS devices that are being integrated in cars such as MEMS, inertial measurement units, environment, TPMS, environmental MEMS for gas and particle monitoring in cabin, and microphones for hands-free voice communication, voice commands, right? So what is the scope for future directions? Vein, vacuum, and tiny umbrellas are reducing the chance of heart attacks. Sorry. Patients will demand better, faster diagnosis and treatment, doctor says. The introduction to nano electromechanical systems, further improvement in the performance, right? So this that's all about my PPTs. Any doubts or any question? Last 1 minute, one question I will take up later in the, I'll share my email ID so you can ask questions because it is already 11:35. At least you need 10 minutes break. By 11:45, next session will start. Any questions? Any questions from the audience?
Sir, good afternoon, sir.
Good
Sorry, good
afternoon.
morning, sir.
Yeah.
Sir, it was a very nice presentation, sir. And I am doing my research work in MEMS area. So
Yeah.
so sir, I have one doubt. Actually, you have explained about the micro cantilever as well as the fabrication techniques and all. So actually, the thing is, I need one suggestion from your side, sir.
Yeah.
Actually, I have done that eigenfrequencies analysis, and then also that HIV, suppose if any molecule is there, how to find out the deflection, those kind of analysis I have
Yeah.
done, sir. After that, actually what happened is I
Yeah.
have just stuck on that point, and even though whenever I am going for any literature survey using different sources, so after that I am
Mm.
not finding the path what to do. And almost in all the papers, the same story has been repeated, it seems, by
Yeah.
changing the languages, or more or less the same thing is happening. So can you please suggest something with your experience or what to do next?
Yeah, actually, this question, what is your area of research actually? What is
MEMS,
the
sir.
title? Okay,
Yeah.
area is MEMS title.
Yeah. Sir, area of my research is means I need to design a MEMS-based device for biomedical applications, sir.
What biomedical application?
Biomedical applications means I want to design a sensor which should be sensed in a faster way. Because in a broad way, I have selected the title because
See, actually, the same type of problem we also encountered in
okay,
one of the student is doing tuberculosis detection using cantilever, right? So most of the time, cantilevers, right, vibrates whenever the surface strain or stress occurs.
yes, sir.
So whenever see, you have to identify what chemical you are using, to that chemical, what chemical you have to apply, so that the stress occurs on the surface of the cantilever. Say for example, antibodies and antigens, right? In the tuberculosis detection, antibodies are placed on the surface of the cantilever, right? Whenever the sample of a person is put on the cantilever, what happens if it gets reacted, right? The mass of the surface of the cantilever increases, and the cantilever gets surface strain or stress, so that it bends. So whenever the cantilever bends, right, the bending moment is shown, that can be characterized in the scanning tunneling microscopy, right? So that bending moment of the cantilever will tell us that there is a reaction occurred between the antibody and the antigen of the particular affected person, so that we can come to conclusion that there is a tuberculosis. So within half an hour or so, we can detect the tuberculosis detection by using a cantilever based tuberculosis, right? I think you got your answer, right?
Yeah, yes, sir. Thank you so much,
Yeah.
sir. Thank you.
So in your application, you have to what sample you have to test. Some chemical reactions you have to do. Whenever chemical reactions occurs on the surface of the tiny cantilever, the cantilever surface gets strained or stressed. Therefore, the cantilever bends up or down. That bending moment itself is the your answer, whether the concerned thing you reached or not. Right? You got it?
Oh, yeah, sir.
Yeah,
Sorry, I can understand, sir. You are running out the time. Last
yeah, yeah,
question, sir.
yeah,
Sir, one more thing I want to ask, sir. Actually, in literature survey, there are a number of problems has been defined,
yeah.
like this kind of biomedical solution, this kind of, and at last they are only concentrating about the deflection or displacement of micro cantilever.
See, this
So,
is
is it sufficient?
no, not sufficient. This is the
Uh,
problem in India. I'll tell you why. Because we are not great at fabrication. Because
okay.
fabrication is the one which is a practical aspect. Right. Simulation is no value. Simulation using COMSOL or Coventor you are doing, and you are seeing the literature survey. That is not enough. Actually, you have to get into the foundry. You have to do the research. So that is the drawback in our India, right? Because I also have the laboratory in my college. It is only a simulation lab, but I can't proceed further to the fabrication because it is costing very huge, right? So you have to get some fabrication papers of your cantilever for biomedical applications, biosensor applications. There you will get the clear-cut ideas, right? So what you have to do some more literature survey on the area, so that you will get the you concentrate more on fabrication papers rather than simulation papers, right?
Okay,
Yeah,
sir. Thank you, sir. Thank you
I
so
think
much,
I
sir.
answered your question.
Yes, sir.
So,
100%, sir. Thank you, sir.
yes, sir. Okay, thank you. and I'll take the questions in my email ID. I will share. I'll ask my colleagues to share my email ID in the group. So all of you, please take up the attend the sessions fully. 80% attendance is very important for getting the certificate. If the talks are very nice talks, you will get from this ATAL FDP. And because the resource persons are, I read in the introduction, so many research eminent personalities are giving their sessions. Please attend all the sessions if possible, right? And try to answer the test. Every day there will be a test. Some 30 questions will be there for 3 sessions, and which will be 1 mark questions. We will share you the Google Sheet. In the Google Sheet, you can answer, and maybe 5 to 5:30 or 6 to 6:30 is the time for answering. You can answer, and automatically that will close, right? And also, I request all of you to give the feedback to each session. Per day, 3 sessions will be there, and first session feedback, second session feedback, third session feedback, 3 sessions feedback, 10 questions we will frame and send you through Google Forms or Google Sheets. So please give the feedback. Once we receive all those things, we will upload that in the ATAL site. Then only they will issue the certificate. So please remember all these things and try to cooperate. And all of you, please join the WhatsApp group, which we have already shared in your email IDs, so that more clarity will be there in communication, right? So with this, I thank each one of you for attending. I particularly thank Kaustubh Kumar, who asked the questions, right? So I thank each one of you, and I thank my management for giving me this opportunity. I thank ATAL, AICT, ATAL resources for sanctioning our this ATAL FDP. So thank you, one and all. Right, I'll be signing off now. So by exactly 11:45, so now 11:30, 11:44, 11:50, we will start the next session. 6 minutes break. So please cooperate. First day there was a function. So to avoid that, to overcome that, 11:50 we will start. Right. Next sessions will be ending at right time. You will get 15 minutes break from each session to each next session. Right. So thank you, one and all, for listening. Thank you.